Morning, everybody. This is Dr. Mahmoud Al-Jaffer from the Princess Sumaya University. And in today's lecture, we will go over the hardware platforms for IoT. So what we'll cover today is what is a hardware platform? What are the types of memory? The power saving technique, the type of sensors, actuators, and the ADC, and the analog to digital conversion, and vice versa. Okay, so when it comes to the program must be built specifically for a particular type of platform. This is where the compiler turns the code into a platform-specific machine language. So when it comes to the hardware platform can be integrated, as we can see in the middle column, where the CPU, the GPU, and the inertial measurement unit are co-located on the same board. And sometimes it's more convenient to modularize the design into main platform, which one or more extension platform are connected. In the example above, we can see that the main platform hosts the controller, a digital signal processor, DSP, that process the information received from the analog to digital converter, the ADC, which will be capable to take the analog signal or an analog feature and convert it into a digital. For instance, it can capture the audio signal. Our audio is analog and will be converted to digital. And we will see that we have here a BLE, which is a Bluetooth Low Energy extension. And this extension platform is attached to the MCU in order to provide some kind of radio transceiving. All right. Some of the examples, as we can see here, we have, like a Firefly development kit. And when it comes like to this type or designing the hardware platform, several factors influence the design of hardware platform depending on the application type, constraints, the budget, different type of microcontroller or the CPUs that are adopted. For instance, for more specific, we're using in generally speaking, we're using either the Arduino as a microcontroller or we're using the Raspberry Pi as a microcomputer. However, for specialized applications, we will have a development board where the GPUs and the DSPs may also be added. Whether the platform is expected to be line powered on battery or or powered by an external power, this will influence the type of application that we're targeting as well as the choice of computing modules. Another factor considered in the design is the type of connectivity intended to be used with the targeted application. Choices vary between wired and different type of wireless solution that only depend on the desired throughput, that not only on the throughput, it will also depends on the energy constraint of the board. How the system will interact with peripherals influence the choice of the IOs. Here we have the GPIO, with general purpose input output, and different type of serial interfaces, such as the I2C, which is the inter-integrated circuit, and the serial peripheral interface, which is the SPI. Consider it as the way that I'm connecting my hard drive. I'm gonna use SATA. I'm gonna use USB and different type of USB, USB-C, USB-A, and so on. In addition to that, you have to consider the debugging. So that's why all the time the debugging is done through the GTAG and the serial connectivity. Consider when you connect to a car. So you have the ODP2, which will allow you to connect, but the type of connection is serial. Okay. Now let's take a look about the microcontroller architecture. And when it comes to the microcontroller architecture, we will basically adopt the Harvard architecture. In the Harvard architecture, separate storage and signal pathway exist for instructions and data. So we have, you see here, instruction, and we have here the data, and we have separate line for both of them. Okay, so we have taken a look about the difference between the CPUs, the MCUs, and the MP system. And you need to remember that the MCU extend the functionality of the CPU that typically handle instruction fetching and decoding and process instructions through the ALU, which is the arithmetic and logic unit. In addition to that, the MCUs incorporates on the same chip the CPU functionality together with the instruction and the data memory and some type of the IO. As I mentioned to you, the example of the the calculators or the switch itself that we've shown. Now, let's take a look at the type of memory. So we have different type of memory options exist to serve service code and data storage in the Harvard architecture. The first type is the double EPROM or the EEPROM, which is usually used to store persistent data given in non-volatile properties, but the content can be electronically reprogrammed. So the consider it as like when you're flashing the BIOS, you can like upgrade it. You can upgrade the BIOS and it will be stored there. Now we have also the flash memory, which is basically faster than the EEPROM, as it is block erasable, that make it more suitable for storing program code that must be run even after the device has been powered cycled. As I told you, like we have the UFEI in the computers, and this has the when you like start a computer, you will see Dell or you see HP. This is where the program of those companies are stored. You know, then we have the DRAM, and the DRAM stands for the dynamic random access memory, and it consists of capacitors and transistors. Because the electric charge of the capacitors decays over time, it has to be refreshed to avoid data loss. هلا الكاباسيتورز لما اخذته بالفيزيكس، اذا ضاع عندنا اي نوع من انواع الباور سورس، الطاقه راح تروح منها. The DRAM is so volatile. That means the data stored is lost when when the circuit is unpowered. Then we have also something called the SRAM, which is the static RAM instead of the static random access memory. Unlike the DRAM, the SRAM does not need to be refreshed periodically due to the by-stable latching circuitry in its implementation. It's also much faster than the DRAM, but more expensive. So, like when you take a look at the gaming RAM, most of them are SRAMs. Now, we have to consider the memory limitation, which is due to the size and the cost constraints, MCUs have limited memory. For example, the STM controller, this STM, which is based on the Cortex architecture. When I say Cortex M0 architecture, it's like when you nowadays when you take a look at the Apple MacBook, which is or Apple iPad, which is based on the M1 or M2 or even M4 architecture, or the phone is based on like the A17 Bionic chip or something like that. So when you take a look at this architecture, you have a 64 kilobyte of flash, 2 kilobyte of double EEPROM, and 8 kilobyte of SRAM. This is very, very limited. Okay. Now, you have to consider the fact that the STM32 architecture, the STM32 controller that's based on the Cortex M0 Plus architecture is used for instance of of wearable device where I would like to save uh, size and energy. And in this situation, when we program it, we need to consider the fact that the instruction memory available has to be limited for 64 kilobyte. I'm not gonna write a code that will be like more than this. Other than this, I'm gonna get an error. To handle this, architecture optimization such as compressed instruction sets are adopted, while further software-based optimization can be used at the code compilation time to reduce the size of the program. Now, let's take a look at the energy consumption when it comes to as hardware platforms for IoT are often battery powered. Energy consumption is an important aspect. This is primarily impacted by the behavior of the MCU, including the power consumption during active period and how frequently the MCU is active. Additional energy might be consumed for cooling purposes that depends on the environmental condition, but also on how much heat the MCU dissipates during the operations. Therefore, optimization can be performed along these three directions. When it comes to a more power hungry processors, is not necessarily less energy efficiency. If it is idle most of the time, we can determine the energy consumed by the MCU with with the formula of this integral. Okay. Now let's consider an example where with two MCU, one that is active all the time and consumes zero point 0.1, but the others is active only 10% of the time and consumes 1 watt when it's active. Now, if we do our calculation, if both run at nominal voltage of 5 volt and powered by um, like 2 ampere battery, the lifetime for both will be 100 hours. Okay. So based on my type of application, based on the class of application, I will select which one that will suit me. Do I need one that's working all the time because I'm dealing with like instant data, or do I need one that will work when a threshold, when a trigger is happening? Okay. Now, also there is something called the power saving technique, different power saving technique, including switching odd peripherals when they are not required to put the MCU in sleep mode. Also, wireless interfaces can also switch off when no communication is engaged. For instance, in the BLE implementation, use functionality that has a power saving mode, which a device wakes up an RF transceiver periodically to send and receive data. Only when we receive data, we will enable the Bluetooth or the Wi-Fi. Another approach in modern is that of reducing and enhancing performance depending on the complexity of the task executed. This can be done through dynamic voltage or frequency scaling. Further power saving can be achieved through software by compiling to optimize bytecode that minimize energy usage. But however, nevertheless, power saving can be taken into account from the chip design stage. For instance, smaller chip with fewer transistors consumes less energy. This is possible with the reduced instruction set computing, which is the RISC architecture. Now, if you take a look at the architecture of the Apple silicon chip, as well as the architecture of the Snapdragon, it's based on the RISC because we're dealing here with mobile devices. However, if you take a look at the architecture of your desktop, the desktop architecture is basically based on the the Intel 64-bit architecture, which is it's like the CISC instead of RISC. It's a complex instruction set computing instead of reduced instruction set computing. And when it comes to the RISC, the large operation are processed in small and simple blocks, keeping the instruction set simple also helps in reducing the power. Okay, so like in this example here, we will see that the MCU typically handle variable workload, and as a result, they do not need to process data all the time. This presents an opportunity for improving the power efficiency, especially for IoT devices that run on batteries and must have reasonable lifetime. Hence, different low-powered modules exist that influence how much of the MCU functionality is enabled and how many stimuli the MCU respond. The price to pay for higher power efficiency, which means a lower energy consumption, is performance. In other words, how fast the MCU processes the data. Performance is also measured in terms of wake-up times. That is how long it takes an MCU to respond to interrupts when operates in a particular low power mode. In the example of the STM32 series of the MCU that are based on the ARM Cortex M architecture, these implement 5 different low power modes. طبعا زي ما تشوفوا انتم مثلا باللابتوب تاعكم لما تفتحوه بتلاقوا في عندكم different power plan. هنا same thing لما بالاس تي ام 32 L0 in this table, in the blue table here, each row shows the performance in terms of one of the key parameters, one indicating the best and 5 indicating the worst. What I want from you is to observe that different performance and power consumption trade-offs are achieved. Yeah, as you can see, if I'm looking for the best performance, the power consumption, look at this here. It's the what? The relationship is axis. See? Okay. Now, we talked about a dynamic voltage. So, workload conditions are often variable. Sometimes you're like you need to do a lot of workload. Sometimes, when there are a lot of objects in front of the camera, the camera has to work um, at the maximum processing in order to detect all of the faces. So that means it's appropriate to adapt MCU performance to the workloads to reduce the energy consumption. Power consumption is directly proportional to the operational frequency and the square of the operational voltage. Therefore, modern architecture, according to this formula, you see, modern architecture employ multiple voltage frequency pairs to scale up and scale down these parameters and thereby reduce the power consumption. And in this slide, we are tackling the sensors. The sensors are objects that convert a physical quantity into an electrical output, such as a voltage. But what they do, they collect data about the ambient environment. The sensitivity of a sensor indicates the minimum input that will produce a given output, such as a microphone will need a certain minimum sound field strength to produce a 1 millivolt voltage. If the output of the sensor is analog, then we need something called analog to digital converter. So the ADC are used to convert this into the signal that can be processed digitally by the the MCU, the microcontroller unit. The core underlying the principle of sensing is derived from a certain physical phenomena. For instance, The Hall effect produces a voltage difference when a perpendicular magnetic field is applied across an electrical conductor, and so on. All right. Now, in this slide here, we have some example of different type of sensor that can be integrated with an embedded system, each of which exploits a different physical aspect. So we have the humidity sensor, we have the accelerometer, we have the temperature, even the push button switch is considered a sensor. And please revisit the slides at which I explain the differences between hard sensor and soft sensors. Now, when it comes to the actuators are is a component of physical system that convert one type of energy to another. Therefore, it requires, as we can see here, it requires what, guys? It requires, like, we need an energy. We take this energy, and this energy, the actuator will convert it into like a new type of of energy. Therefore, the actuator requires a signal and a power and energy source. For instance, the actuator can take the order to or can be triggered in order to open a door. Therefore, it has some hydraulic movement. Now, when it comes to the different type of actuators, we have the electric actuators, we have the pneumatic actuators, we have the hydraulic actuators, and the thermal actuators. Let's start by tackling what are the electrical actuators. Now, like the electric actuators, they convert electrical energy, AC or DC, into motions. They are widely used due to their precision and control. For instance, the DC motor, like like إذا عندك أنت درون ولا إذا عندك لعبة، تمام، based على أنت شو بتضغط بالكنترولر، سرعة الموتور هاي لازم تتغير. So used in drone to control the proper rotation. And we have also the AC motor, which is found in many industrial fans and conveyor belts. In addition to that, let's not forget the solenoids, which is used in electric door locks to control locking and unlocking mechanism. Now let's take a look at the pneumatic actuator. Now those pneumatic actuators use compressed air to generate motions. They are known for their simplicity and their reliability in system requiring high-speed operations. من الأمثلة على البنيوماتيك actuators are the air brake اللي هون اللي عنا, which are found in heavy vehicle like buses and trucks. like يعني بتشوفوا في التراك في إلهم مثلا صوت عند البريك. في ناس بفكروا إنه this is hydraulic. No, this is not hydraulic. This is pneumatic. And the pneumatic cylinder, which is used in the robotic arm for gripping or lifting tasks. And we can also use them in packaging mechanism, which can control the movement of packages using pneumatic system. Now let's move to the hydraulic actuator. Now those actuators, instead of like using the air, they're using what? They're using liquids, and like the type of liquids is commonly oil, as we can see, and under high pressure they produce motion. They are ideal for application requiring high force, such as hydraulic crans, which are used in constructions to lift heavy loads, hydraulic jacks found in car repair shops for lifting vehicles, and excavators, which are hydraulic systems, operates the digging arm. Now the thermal actuator, those type of actuator use heat energy in order to generate motion.
typically for applications requiring temperature-sensitive operations. For instance, we have the thermostatic valves, which control water flow in heating system based on temperature. We also have the thermal switches, which use automated engines to regulate cooling system. Lastly, في عنا الفاير سبرينكلر سيستم. هذا الفاير سبرينكلر سيستم بيكون طبعا دائما مربوط مع شو مع سموك ديتكتور ولا مثلا فاير الارم which activate the sprinklers اللي هم الرشاشات اللي بيرشوا المي when heat threshold are reached. Okay, now let's address a different topic, which are the input and output we've seen in the development kit. So basically, I/O is required to be able to sense the environment and interact with it. A range of interfacing and communication protocol exists. طبعا similar مثلا الجهاز في عندنا كويس بنقدر نشبكه عن طريق اليو اس بي، عن طريق السيريال بورت، عن طريق الساتا بورت، عن طريق الام دوت 2. All right, now what this communication protocol, they are ranging here when it comes to IoT from a serial TX and RX protocol such as the UART مثل هذا اللي هو في بيكون في عندي هون TX وهون عندي RX، تمام، sender و receiver that allows two devices to exchange data in form of packets asynchronously using two wires at the speed of السبيد اللي هون راح يكون في عندنا شيء اسمه الباود هير like باود ريت. طبعا هو بتكون هون السبيد هون maximally we can be 15200 pound. The UART transmitter converts the parallel data from the MCU into serial data before transmission. A UART receiver performs serial to parallel data conversion at the receiving device, and the data flows from the TX pin of the transmitting UART to the RX pin of the receiving UART. طبعا هذا هو البيسك form للcommunication. We have a more sophisticated peripherals and requires, for instance, a wireless transceivers. Therefore, we go with what? With the SPI to communicate with the MCU. This establishes a master-slave relationship, but by which an amount of data can be transmitted into a continuous stream in both directions according to the clock discipline. طبعا اللي بأخذوا digital logic بيعرفوا انه يعني through the trigger of the clock بصير في عندي الستريمينج للداتا. The data can be transferred without interruptions in a single master single slave configuration. The pin configuration is as the following. We have the master output slave input, which used by the master to send data by the slave. We have the master input slave output, which is used by the slave to send data to the master, and we have the clock which is distributed by the master in order to make sure that the data is synchronized. And lastly, we have the slave select chip, which is used by the master to select by which slave to send data. Sometimes we have multiple slaves can be connected in parallel or in a daisy chain if the master has a single chip. This is when it comes to the SPI. Also, we have here the I2C. I2C here we can see إنه في عنا ascending and receiving a bidirectional wire here بال I2C. This is how it can differentiate عن ال UART. So the I2C works the UART in the sense that the data is sent in packets, but in a synchronized fashion like the SPI. Two wires are used between a master and the slave. Through the master can support multiple slaves. Serial data is used for data exchange, and serial clock is used to carry the clock signal. The packets are delimited by the start and stop condition, and the first 7 to 10 bits that are used to identify the slave address. All right. And then we have, those are the most, well-known one, the GPIOs, the general purpose input output. هدول بنشوفهم كتير بالراسبري باي. All right. طبعا they are less restrictive, and they allow the system designer or integrator to define the behavior of the IOs. Okay, so the general purpose input output is digital signal pin, whose behavior can be controlled by the user either to output a certain voltage level, usually low or high, so as to derive a peripheral or to serve as an input, such as receiving reading from the sensor, which can be a temperature or accelerometer. The GPIO pin also be used to what here, like can be used to receive interrupts. So the interrupts, for instance, can trigger the MCU or wake it up from a specific sleep mode. The GPIO pins can also be grouped here, as we can see. We can group them, grouped into a port, typically like with 8 pins, لانه بدنا يكون عندنا 1 byte يعني تمام, and subsequently controlled as a group through a dedicated instruction to control linear processes. For instance, in motor, pulse width modulation is applied. We will explain pulse width modulation shortly. And the GPIO output typically produce low currents in order for milliamps, in the order of milliamps to 10 of milliamps. If higher currents are desired to derive peripherals such as motors, additional circuitry based on transistors and relay is used to amplify the output. طبعا الريلي بفوت عليه low voltage وبطلع عندي high voltage, وبالتالي بتزيد عندي الكرنت. طبعا بالpulse width modulation, let me tell you what about the pulse modulation. The PWM is typically used when the MCU needs to output a variable voltage by switching between high and low voltage very fast, طبعا في اشي اسمه الديوتي سايكل. طبعا السيجنال هي هاي السيجنال. طبعا الديوتي سايكل فيها 100%. What is the duty cycle? The duty cycle is the fraction of one period t during which a signal is active. طبعا لاحظين انه السيجنال هنا active all the time. هلا اذا كنت مثلا شابكين for instance an LED على هذه السيجنال بتكون light all the time. طيب لو شبكت هذه السيجنال, do you think انه على LED انه راح يصير يطفي ويشتغل؟ هذا in reality الحكي مش صحيح, لانه as a human we will not notice the high frequency. However, we will see that انه الضوء ال LED اللي عندنا صار يشتغل لكن ببرايتنس equal to 50%, يعني بنص الاشاره بنص الاضاءه اللي عندي. هنا بنلاحظ انه الضوء خفت بنسبه 75%, لانه الديوتي سايكل هي 25%. سيميلرلي كنا شابكين مارر, طبعا بتكون هون عندي الماكسيمم ار بي ام لنفرض انها 1000. طبعا كويس, هون لما اشبكه فبتكون الار بي ام اللي هو روتيشن بير مينت راح يكون عباره عن 500, وهون راح يكون عباره عن 250. طبعا those are some rules that you need to revise, at which the duty cycle will equal to the PW over T ضرب 100%, where PW means the power here. The frequency, all the time, the frequency is 1 over T, which is the period, and the average voltage here is equal to V average multiplied by D over 100. So D again, D is the fraction between the pulse width here over and the period. Okay. All right. Now let's take a look at something else called the analog to digital converter. ADC is required to transform the analog output of a sensor into a discrete value signal that can be processed by the microcontroller. We know that the microcontroller are based, or the microprocessor are based on transistors. They only understand digital. Therefore, we need something to convert the analog. وطبعا مثلا التمبريتشر هي انالوج، الاضاءه طبعا الضوء لما يفوت عندي كويس، لما انا اعمل مثلا فوتو ريزيستنس او اعمل اشوف اذا في عندي ضوء ولا لا، هذا برضو انالوج. اذا مثلا في عندي على سبيل المثال الاكسلوميترز، this is analog. So I need to convert it. How I'm gonna convert it? Through something called sampling. All right. Okay. The process is known as sampling and involves recording the input signal amplitude at a discrete time interval. لاحظين انه انا ما خليتها continuous like this. انا كل فترة اخذت sample، يعني قسمتها. طبعا the more the more sample I will take, the more resolution is I will get. يعني مثلا إذا كان عندي بس أنا باخذ 3 samples, I will lose a lot of the characteristic لهاي السيجنال لو أخذت بس هذول 3 samples. بينما لاحظين هون كان ماخذين إحنا samples كتير، therefore إحنا at least we can we can capture the characteristic of this signal. All right. The period between two samples is dedicated by the sampling frequency that plays a crucial role in reconstruction, as we will see shortly. The sampling can be achieved with a sample and hold circuit that loads the voltage into a capacitor as provided by the transistor. هون عندنا كيف عندنا شو. This is the circuit that's used. هون بيكون في عندي الانبوت بيكون analog والاوتبوت راح يطلع عندي راح يكون عندي discrete راح يكون يعني limited. An operation amplifier here, the op amp هذا this is the operation amplifier بالelectronics راح تاخذوه. Is acting as a buffer, is used to transfer the recorded voltage to the output and ensure the voltage across the capacitor is proportional to the input. Also, we have something called, aliasing. Okay, so the phenomena by which two sample signals cannot be differentiated is also known as aliasing. Reconstruction of a signal that was subject to aliasing can lead to a version that's different to the original. So to avoid this, what will be the solution? ADC designer, analog to digital converter designer, must take into account the Nyquist criteria. This proves theoretically that an input signal that has meaningful spectral components above the sampling frequency will be subject to aliasing. طبعا شو الالياسing؟ انه شو هي النايكويست؟ النايكويست هو تستخدم لحساب الباندويث. في عندنا نايكويست وفي عندنا شانون. But they are outside the scope of this. I want you to understand it. Like each time when I would like to do the sampling frequency should be لازم دائما should be at least twice the highest spectral. يعني اعلى spectral عندنا اعلى component بدي اضربه باثنين مشان to make sure انه I'm gonna avoid the aliasing. All right. Any discrete signal has a space, has a time, has an intensity, as well as has jaggies, and finally has high frequency informations and appears as low frequency information. So if I'd like to reconstruct my signal when I convert it to the frequency domain and send it, if I would like it, I need to make sure that I have, I did the sampling with twice of the maximum frequency presented in the signal. So the continuous time signal can be completely recovered from its sample if and only if the sampling rate is greater than the twice the frequency or the maximum frequency present in the signal. Like, to understand that, if we take a look here at, at this example, if we take a look here, so we will see that here we only considered, the FS sample is less than the twice of the frequency, because like only we took just one at each time from each sinusoidal, but if we take a look here, we took like 2, all right, and therefore the Fs is equal to 2 of the frequency. However, here is we gonna get what we will be able to reconstruct the signal. Look at this continuous signal, and this is the discrete. And if I if I missed if I did not follow a Nyquist and Shannon theorem, my signal will be not similar to what? Not similar to the continuous original signal that is here. Like, look, here it's a continuous, and here is a continuous, and here I took only the frequencies, and this is the effect of aliasing. All right. Okay. Now the second step after the sampling is the quantization. So this quantization meant to restrict the sampling values to countable set that can be represented on a number of bits. This is achieved either by rounding on truncation of sample values to the nearest element of the quantization set. Inherently, this introduces some error that also impact on the reconstruction. So if we take a look at this circuit now, this is a schematic of a 3-bit quantizer that use 3 comparators to match the input to one of 8 possibility voltage level in the range of 0 to volt references. So if we take a look here, let's take a look at here. Now, how many, we will see that we have 3 operation amplifier. And what does that mean? What does that mean? That means I have 2 to the power 3, which is 2 to the power 3. This is equal to 8. That means I can, any signal, I can take 8 levels of voltage to represent them in a discrete way. So this is from V0 up to V7, all right? So the V reference, whatever the continuous value from 0 to V reference will be equal to from V0 up to V7. So if it's for instance, if it's more than 5.5, I need to make it 6. If it's 5.1, I have to make it V5, and so on. So let's take a look at the resolution in the next slide here. So the number of bits used to quantize the sampled analog signal dictates the precision of the ADC. As such, the resolution of the quantizer is computed as the ratio between the voltage range and the number of levels that can be represented. So as we can see here at this, in this figure, we have the 3-bit. That means any values, I can match it between 0 up to 7, I'm not gonna consider 8. And the resolution, in volt, can be expressed with this formula, which is Vmax minus Vmin over 2 to the power n. What does that mean? That means if let's say that the values of the V maximum is equal to 5 volt and V minimum is equal to 0 volt, all right? So what does that mean? 2 to the power, like it's gonna be like each step here that I can consider, it's gonna be 5 over 8, because 2 to the power 3 here is equal to 8. Okay, so like each time I will consider, you know, the differences here by this value. Those are the steps. So this process introduces quantization error that's typically computed by subtracting the output of the ideal analog to digital converter from the output of a digital to analog converter that performs the inverse process. The quantization error is typically in the range of, like usually, like, you know, the range, yeah, like I can, like, you know, like say that, you know, the error is equal to plus minus fs over 2 to the power n plus 1, all right, where fs is the full scale, all right? Now, and finally, like, you know, there is something called SNR, or the SNR is the signal to noise ratio. So therefore, to assess the goodness of the analog to digital converter, designer usually measure the impact of the quantization error through the signals to noise ratio, that is effectively the ratio between the signal voltage range and the amplitude of the noise. All right, now the signals to noise ratio is, you know, like is a ratio, there is no unit. However, if I convert it to decibel, dB here, I need to take the log 10 and put the voltage of the signal over the voltage of the noise and multiply it by 20. Okay, so the ideal ADC can be characterized by an SNR value as expressed above, all right? So if we have an example, the ideal 8-bit convert has an SNR value equal to almost like 50 decibel. And finally here we will, like, you know, as like sometimes we are while we usually convert signals from the analog to digital so we can process them, sometimes I need to project them or to output them into what an analog device, and hence I need to get a digital to analog converter. What it's doing, like, you know, the digital to analog converter translates a digital signal into a corresponding analog voltage, and some DACs can also produce complex waveform. In some application, it can be more convenient to use PWM instead of the introducing, like, you know, pulse width normalization, you know, instead of introducing additional DAC circuitry. For instance, when the output of the MCU is only meant to drive the input to a motor or gradually decrease the voltage to dim an LED. Therefore, like, you know, the pulse width modulation can mimic and can emulate the process of converting digital signal to analog signal. As we will see, like, you know, in the Raspberry Pi, we have no analog signal. Therefore, if I would like to produce a signal that mimic the analog behavior, then I'm gonna use the PWM. There are several metrics that quantify the performance of the DACs, and some of these are application dependent. Some important ones include the dynamic that represent the differences between the extreme values of the voltage that can be produced. Another indicator is that the resolution, similar to the ADC, you know, so the voltage range that the DAC can produce, as well as the resolution.
which measures how many levels can be produced at the output. In some application, such as audio and video, this is also determines the depth, which can be indicated by THD here, THD plus N, which is the depth plus the noise, which is at the measurement of the percentage harmonic distortion and noise presented in the reproduced signal. Therefore, therefore, the DAC performance indicators, or the key performance indicator for the DAC are, if we take a look here, are the dynamic range, the resolution, and the depth, which is the THD plus noise. All right, that's it for today, guys, and I will catch you in the next one.